Good morning, everyone. I will start sharing the screen. Start in a minute. Yeah, I guess all of you can see this. So this is the proposition we proved in the last class. So if you have a convex function and xn is a martingale and such that the integrability conditions are satisfied, then f of xn is a submartingale, and consequently mod xn is a submartingale, and also xn squared is also submartingale whenever the second moments exist. Okay. So the proof uses basically Jensen's inequality for conditional expectation. So that also we had seen. All right. So today we will look at stopping times. We have already seen this in the context of Markov chains earlier, some examples. So this is a more general setup. So you remember all our martingales are defined with respect to some stochastic process. So let yn be a stochastic process. And suppose capital T is a random variable such that it takes values in non-negative integers and also possibly the value plus infinity. We had seen similar things happening even in the context of Markov chains. Okay. And for each n, of course, finite, the event t equal to n is determined by y0, y1, yn. In other words, if you know the values of y0 to yn at a particular omega, then you can, from that you can tell whether t omega is equal to n or not. Or rather, t omega is less than or equal to n or not, or greater than n or not, and so on. So that is what we have written here. So in such a case, this t will be called a stopping time with respect to yn. Of course, sometimes it is also called a Markov time. It is not any random time. It should satisfy the second property crucially. So as before, as per our convention, any reference to yn would be omitted if it is clear from the context. Please note it down if you want. Okay. So as before, the key point is to determine if t equal to n or not. One need not require the knowledge of the future time points. Actually, it would have been better to use here instead of the subscript n, something like L or something. L or L greater than or equal to n plus 1. You need not know.
So can you go to previous slide again? Previous slide.
Yeah. Note it down if you want.
Okay, got it.
Yeah. So this is, you don't need to have any knowledge about the future time points. Right? Please replace this n by some other symbol so that there is no confusion. Okay. So to indicate these things, it is sort of better to write it this way. Indicator function of the set of all omega such that t omega equal to n. That is what t equal to n means. So the value of that function at an omega, that will also be a function of composition of y1, y2, yn and this indicator function. So this function on the basic probability space omega is a combination, is a function of y1 to yn and this indicator function on that. So if t omega equal to 1, this is equal to 1, and if it is not equal to n, this is 0. This is the convention. I mean, it's a natural definition, you can see, under the context. So consequently, you can write the function indicator of t less than or equal to n as summation k going from 0 to n of these guys, with k varying from 0 to n. And of course, indicator of t, big capital T, strictly greater than n is 1 minus this function. Okay, note it down if you want. Okay, a simple exercise. Show that t is a stopping time with respect to these YLs if and only if for every n, the event t less than or equal to n is determined by this. And of course, that is also equivalent to for every n, the event t strictly greater than n is determined by this. And as a first example of a stopping time, t constant, t equal to, identically equal to k. K is a fixed integer. So this takes the constant value. So you can easily see it is a stopping time. Okay. So next example, or rather next class of examples, is a so-called first entrance time. So Xn is a stochastic process such that for each fixed m, Xm is a function of y0, y1 to ym. So in other words, this kind of things will be applicable to if the case when Xn is a martingale with respect to the Yns. So some of these entrance times could be in terms of these Xis. So let A be a subset of the real line. The first entrance time of the process Xn into the set A. So that is defined by T sub A at omega equal to minimum n greater than or equal to n, such that Xn omega belongs to A. And as we had been following earlier, this is equated to plus infinity if there is no n satisfying this condition. So the entrance time differs from the hitting time in here. The hitting time, it was only greater than or equal to 1. Now it is greater than or equal to 0. Note it down if you want. So note that T sub A of omega is equal to n if and only if xj omega does not belong to A for j equal to 0 up to n minus 1 and xn omega belongs to A. Consequently, this T sub A is a stopping time with respect to the stochastic process xn and hence with respect to the process yn. So as we had seen in the case of the Markov chain, etc., for any fixed integer k greater than or equal to 1, the kth time the process xn visits the set A can be, you can show it to be a stopping time. It's an exercise here for you. Can be shown is again a dangerous phrase. Sorry. Note it down if you want. So let xn and A be as before. Now we consider the hitting time. So the first hitting time of the set A by the process xn is defined by h sub A at omega is minimum n greater than or equal to 1, such that xn is in A. As before, there is no such n greater than or equal to 1, then this is plus infinity.
Sir,
Yes.
so am I audible?
Huh?
Am I audible?
Yes, you are audible. Yes.
Okay, so I just had a question. So in the definition of H sub A of omega, it should be of xn of omega, right? Within the bracket. Minimum of n greater than or equal to 1, xn of omega belongs to A.
No. What this is, hk is a function defined on the sample space capital omega.
Yeah, that I know, but in the definition of H sub A of omega, it would be minimum n.
No. This omega here x, you mean here x and omega. That's what you mean, right?
Yeah, here also it will be xn omega.
Yeah, here it will be x and omega. It will not be here. It need not be here. Because for example, h sub A omega may be equal to 1 or
Okay.
2. Whereas x and omega takes a fixed value, right?
Okay. So that's why instead of writing xn omega, we write simply xn.
We generally don't write H sub A of xn. We write H sub A. If you write put within anything, it will be omega, not xn omega.
Yeah, that I know. But so when you are writing HA omega, but why are you not writing xn of omega? Because xn is also a function on the sample space.
Yeah. So here it is a typo. You can fill it in here. Yes, you write omega here. Yeah.
Okay, so we can fill it omega here.
Yeah.
We can fill it omega.
Yeah.
Okay, fine.
Mm-hmm.
Okay. Just to clarify that. Okay.
Yeah, sure. Yeah, okay. Sorry for this slip. Okay, please fill it in. Yeah, as he has pointed out, put a omega here. Okay. So for each n, note that h sub a omega equal to n if and only if xj omega is not an element of A for j equal to 1 to up to n minus 1 and xn omega equal to A. Note that here we are silent about what happens at x0 omega. So H sub A is a stopping time with respect to xn and hence with respect to yn. So note that it is possible for x0 omega to be a member of A, but still HA omega equal to plus infinity. Say, for example, you can easily construct a transition probability matrix. Let us say state space is 1, 2, 3, 4, 5. And corresponding to 1, once it starts from 1, let us say it goes to 2. And the column corresponding to 1, that is the first column, has all entries 0, which means from nowhere you can go to 0. Sorry, nowhere you can go to 1. So in such a case, for the A equal to the singleton set 1, HA will be 0. T sub A, that is the entrance time is 0, but hitting time is infinity. That is that Markov chain. Once it leaves that state 1, never comes back to 1. So the entrance time and hitting time, can be quite different.
Sir, I have a question.
Yes.
So is there any definition of second hitting time, third hitting time, etc.?
That is what we have seen in the Markov chains course also. No, same thing. Because that is why the second hitting time and all, we say that n minus 1th hitting time plus 1, minimum n greater than or equal to 1 or something like that, or greater than or equal to that quantity. You go back to that definition.
Okay.
Similar definition you have to give.
Okay. Very first time after the first hitting time, it reaches the state. It is called the second hitting time and on.
Yeah, that's what you had seen, right? Note it down if you want. See the stopping times according to some famous probabilists or the probability theories tool to tame randomness. Of course, that may have a lot of exaggeration, but yeah. So this is also continuation of the previous slide. So we have seen the first and kth hitting times of a set in the case when xn is a Markov chain.
So just to clarify, get my doubts clarified.
Ah.
So stochastic process is just a collection of random variables, right?
Yes.
Okay.
But see, the interesting, I mean, rather if the stochastic process is it is a collection of random variables, that is a general definition, okay, or general intuitive this thing. But if you want to use that kind of a construct for drawing certain inferences about nature or certain phenomenon under consideration, there will be, or that is would be interesting things only if there is some kind of interrelationship among the random variables, right? And certain types of relationships are a thing which have proved to be mathematically amenable are the Markovian property, martingale property, and of course, this kind of process we have not seen, stationarity property in the sense stationary processes. So stationary process, you can view roughly that something like a Markov chain, which is the starting point itself is the stationary distribution, things like that. Okay. So if they are completely random, there is no connection, then that is not a kind of situation where you can draw any meaningful conclusions. Like even, for example, in your differential equations and things like that, you have to have a relationship which sort of gives you a connection between the how the particle moves or how it evolves over time or over some other variable which may be considered independent variables. So then you can investigate, or perhaps if it use it for predicting certain things. After all, some of these things are the end result is that you should be able to make certain predictions about what might happen in the near future. Of course, stationarity means far away in the future. That is all theoretically. Then, of course, there are a lot of other questions, especially computation-oriented thing. How fast will the convergence take place, and certain algorithms, how will it work? So those things are all, that is another, I mean, completely different ballgame, if one may if I use that kind of a phrase. And if a particular, let us say, kind of situation is not amenable, then of course you go one step further, invent the type of mathematics which is required. And sometimes the situation on hand might indicate what kind of new mathematics might be needed, perhaps, who knows. Okay. Yeah, now we will look at something which I might have even mentioned earlier, something which is not a stopping time. So this is not to be considered an example, maybe a counterexample. Okay. So let eta of omega denote the last time hj omega is in A. So for any fixed integer n, to determine if eta omega is equal to n or not equal to n, we need to know about the entire future trajectory. J greater than or equal to n. So the last time the process visits a fixed set A is not a stopping time. I think I might have made a similar statement in the context of Markov chains also. See, even in many other branches also that is true. No, if you just have a set with no structure, there is no interesting information obtainable from there. You may need perhaps some algebraic structures like a group property or rings or fields and so on, or some analytic property about continuity or differentiability and things like that. So there has to be some kind of a relationship.
Sir, I have a question.
Hmm.
So basically this parameter eta of omega may not always be well defined, means it can be infinity also.
It can be infinity or it can be finite. But see, the thing is,
Okay.
suppose if you want to say that for a particular omega, the last time it visits is 10.
Okay.
So just knowing the process up to time 10 is not enough, right?
Yeah, because we have to ensure from 11 to infinity.
Yeah, so it does not satisfy the property that is dependent for any n only up to time n.
Okay. But I have a question. So if suppose if A is a singleton set, okay, and that if that particular state is a recurrent state, then eta of omega will be infinity, right?
Yes, of course.
Yeah.
But then
Means for a recurrent state, there will be no last time defined as a finite value.
Because in that case, you have lot of information with you because you know that the process is recurrent.
Recurrent, okay.
Okay, a priori, you have lots and lots of information.
Okay. But can we make such conclusion for transient state?
For transient state, you generally cannot because almost every trajectory will have a last time.
Okay, but can we say that eta of omega will be finite for a transient state?
We have proved such things, no? The number of visits is finite with probability 1. Given wherever first various equivalent conditions for recurrence and transience we had proved, we have shown that the number of times the thing visits a transient state is finite.
Okay.
So if you know something is recurrent or transient, that means in your hand you have a lot of information. And similarly for two random variables, if you know that they are independent, you have lots and lots of information. Okay. So some of these, for example, independence assumption and things like that are made in many cases as a first approximation to study something which is unknown. See, like if you are going into a dark room and let us say, of course, there assume that there is electricity and so on, and you are looking for a switch. Your first approximation of this thing is that the switch will be somewhere near the door. So you sort of this go to the wall and at your height or level, you sort of see, probe like that. Because things having independence property and things like that, lots of things have been studied already for the last 200 years or more. Ever since statistics was studied as a subject, and probability theory also sort of enhanced statistics and things like that. And also perhaps in practice, people found that certain characteristics seem to have no relationship with other characteristics. So, okay, the independence assumption might be not unreasonable in such a situation. Okay. So what I'm going to state, certain things are facts. You can also in your notes write within bracket exercises. So S and T, let us say, are stopping times. Of course, with respect to yn and things like that. Then S plus T is also a stopping time. That is because you can write the indicator of the set S plus T equal to N as a summation K going from 0 to 1 of indicator S equal to K product indicator T equal to N minus K for any N. Okay. Similarly, the minimum of 2 stopping times is also a stopping time. Whenever you have minimum, considering minimum, it is always advisable to take S minimum T greater than N, because then that will be the product of these two indicator functions. Please note it down. Okay. So as a consequence of this, if you have a stopping time T, and we already know that the function which is identically K, that is also a stopping time. So the minimum of T and K is also a stopping time for any fixed K. So T minimum K at an omega will be T omega if T omega is less than or equal to K. And if it is strictly greater than K, it will be K. And similarly, maximum. And for maximum, this S max T less than or equal to N, you take S less than or equal to N and T less than or equal to N. It's a product of these two indicators. This kind of things you also would have seen in examples where you want to consider the minimum of two random variables or maximum of two random variables and things like that. Geometric, exponential, and things like that are usual things which are amenable to this kind of reasoning easily. So you would have also got questions related to it.
So what exact properties are you using to show that LHS is a stopping time? You are using that RHS is dependent on everything less than equal to n, right?
Yeah. So that is basically in this, for example, you have to see that this function is expressed as the indicator of something which depends only up to the for any n up to n. Okay.
Yeah, got it.
Yeah. Like say basically we are something which we had written earlier, no? Yeah. Sort of that is the formal way of doing. You can intuitively, you can sort of even intuitively argue and see. Okay, and then that is why that is how these things are guessed. Okay, please note it down. If you want me to go back to the previous slide, I can do that. Okay, now we will look at the, say, the process x sub t wedge n. So remember, we have already observed that if t is a stopping time, t wedge k, that is minimum of t and k, is also a stopping time. So now we let us say the process x is fixed, some stopping time t is fixed. Let us say n is going to vary. In other words, something which instead of stating it as a proposition and proof, the proof is going to come first and then the proposition for a change. So let xm be a martingale. Of course, everything with respect to some process yl. And t also a stopping time, both with respect to yl. So for each fixed k running over 0, 1, 2, etc., one knows that t wedge k is a stopping time with respect to this y. So for example, let n be fixed. Define first the random variable t sub t wedge n by this is equal to x t sub x sub t omega evaluated at omega. If t omega is less than n, and this random variable is the value, takes the value x n omega if t omega is greater than or equal to n. Of course, at t omega, both these guys agree. So there is no inconsistency in the definition. I mean, that x sub t wedge omega we have defined in the most obvious way.
Then it's a stopping time, right?
Pardon?
X is a stopping time.
Where is S here?
X.
X is a martingale. X, we are starting with the martingale X.
No, the random variable X, T, and N.
No, see, X is a stochastic process which is given to be a martingale.
Yes.
T is a stopping time. T is a stopping time means for each omega, it has a integer value. Okay. See this.
Okay, got it. Yeah, it's confused. Okay, I got it.
See the point here is, in this case, say for example, you can take.
N need not be an integer valued.
X need not be integer valued.
Yeah, exactly.
Of course, since in this course we are considering the discrete time martingale, generally they are sort of, you may, without lots of generality, you take it to be integers, but they just have to be some finite or countable state space. Okay. So the point is, in this random variable, we are if t omega is a constant, let us say 10, it will be x sub 10 omega. But what happens is, this guy also depends on omega. Yeah, this t at omega will always be an integer. Of course, if it is infinity, then this will not generally be defined. It will be left undefined. So generally one can talk about this when the stopping time is finite. That is one way of making it finite, is to consider t wedge n. And as n goes to infinity, see what happens. Then one can talk about the value that consider the final, this random variable only on the set where t is less than infinity, as one may see later. Okay. Whereas t wedge n, since it is t wedge n will always take value less than or equal to n, this is well defined. Yeah, please note it down. Okay. So we want to show that the process x t wedge n, as when varies, is also a martingale with respect to y. So for this, we define one random variable which is I sub n. I sub n is a function which is defined on the basic sample space omega. So I sub n omega is taken to be 0 if t omega is less than n, and it is equal to 1 if t omega is greater than or equal to n. sort of to correspond to this kind of situation. Sorry, note it down if you want. Okay. Note that this in omega for any fixed omega is equal to 0 if and only if t omega is strictly less than n. That is, if t omega is strictly less than n minus 1. So, if for a particular omega, actually I could have perhaps written in omega equal to 0 can be determined by observing yn omega, y0 omega, y1 omega, yn minus 1 omega, as t is a stopping time. And since in omega is equal to 1 is equivalent to in omega not equal to 0, this also can be determined by observing up to n minus 1. So that is why here we have defined it this way rather than less than or equal to n and greater than n. So some of these things are subtle, so that there are reasons for making this. Consequently, this I sub n is a function of y0 up to yn minus 1, n here and n minus 1. Note it down. Okay, yeah. Fairly obvious claim. X sub t's wedge n at omega is x sub t wedge n minus 1 omega plus I sub n omega of the difference. I think it is pretty obvious with the way we have defined in omega. Anyway, proof. So suppose t omega is strictly greater than or equal to n, then in omega is equal to 1. So in that case, x, this left side here is xn omega, and this is xn minus 1 omega. So consequently, in that case, the claim follows. And similarly, you can dispose of the case t omega strictly less than n. In that case, in omega is 0. So this is equal to this and this. So armed with this, the defining property of a martingale is easy to prove. So from the claim, and of course, these things are functions of y0 to yn minus 1. So we can write this way. This is from the claim, and this is a function of these guys up to n minus 1. So that comes out. And here, this thing is a function of these guys. So that comes out of that conditional expectation like a constant. That again, you can refer back to the properties of conditional expectation. And finally, you get this is equal to 0 because xn is a martingale. So we get again is a verify that. So we have proved what we wanted to. Xm be a martingale and t is a stopping time. Then the process x sub t wedge n as n varies is also a martingale with respect to yl. And in this case, an immediate corollary is if you take since this is a martingale, by the property of martingale, the expectation doesn't change. So expectation of x sub t wedge n is same thing as expectation x0. So this is just how to define x sub t omega. X sub t omega is given by this. So that is xt omega is equal to x1 omega when t1 omega is n. And this is defined only when t omega is less than infinity. So we will stop here. In the next class, our aim will be to extend this conclusion for a stopping time. Under what conditions? That will involve some conditions concerning t and so on. So that we will see in the next class. That's called optional stopping theorem or optional sampling theorem.
So when will be the last lecture?
Last lecture, probably, I hope, most probably one more lecture I will need. I thought I will need 2 or 3, but what I have decided is I will have one lecture, and the other one which I want to do, or rather this thing is that the proof of that theorem concerning limiting distribution, aperiodicity, that involves measure theoretic ideas. So what I will do is the proof of that I will just write down the notes and upload it, because that is not included for your exam. So those who are
with the exam?
Huh?
When will be the exam?
Exam I am planning for 30th of December. 30th of December, 10 to 1. Yeah, I was about to tell you that before ending the session today. Good that you
So
asked.
when is the interim exam? Can you once again?
Sorry?
When is the interim exam?
End terminal exam.
When is the interim exam?
Yes, end terminal exam is going to be December 30th, 10 to 1.
So is it possible for you to have it a little bit early if
no, it is not possible because I am not free.
Okay, fine.
The only earlier thing I can prepone is 29th.
But the portion will be over by next week.
Portion will be over very soon.
So, sir, how many more lectures are remaining? 2 to 3 lectures.
That's what I told just now. See, 1 or 2 more lectures. Initially, I thought 2 or 3, but I think I can finish it in probably 1 more lecture. And the remaining certain thing, I will just give the notes. That is the proof of that limiting this thing for the Markov chain under a periodicity.
Okay, but that will not be included in the end.
That will not be included in the exam. That is why I am thinking of only giving the notes for it and not having a lecture or a class. Okay?
these was they are not included in the exam. Okay, fine.
Yes, yes. But doesn't mean that you don't have to go through it. I have some curiosity. Okay.
No. I am just asking.
I am just joking. Yeah, sorry.
I'm just asking.
Yeah. Be curious. Sure. Okay.
Yes, sir. Obviously, yes.
So we'll stop sharing now. So all of you, please take care, and we will see next week. Okay. Thanks.